kinetic energy. Yesterday we were reminded that kinetic energy is what? Energy in motion. And potential energy is? Has the potential, and so without using the same word, we would say stored energy. Okay? So mechanical energy is the sum of kinetic and potential, the two overarching umbrellas. It's the sum of the two of them together, and we find it with the most general formula. Mechanical energy, listed with an M, is equal to EK, which is representative of kinetic energy, plus EP, which is potential energy. And so how do we solve for EK? What's the formula we were reintroduced to yesterday? No, EK. 1/2 mv squared is EK. And EP was what, Avery? mgh. Okay, so we've learned those two basic formats. If we had spring energy, do you remember what that formula is? Kx squared. Yeah. Okay. So the law of conservation of energy is in isolated systems. Okay. It can't be. It's a theory. It's not a practical thing. It can't be in non-isolated systems. And so the object has to remain constant, and it's as the object changes position. So if we're changing position, is that distance or displacement? But when we're talking, we've evolved from the two words from kinematics to now. If we're talking a change in position, you're not wrong, Daniel, but the better answer is displacement. Okay? Because distance is strictly the sum of all the steps that you took on your walk, whereas displacement indicates a change in direction. Okay? Kinetic and potential energy simply swing backwards and forwards from each other. If you're in motion and you come to a stop, you're now at potential energy. If you're stopped and then you start moving, you go from potential energy to kinetic energy. So the definition of an isolated system is where neither energy or matter can enter or leave the system. Okay, this is key because there's a difference between a closed system and an isolated system. In an isolated system, neither energy or matter can leave the system, which means that there's no external forces acting on it. Okay? So let's look at an example. One example that represents graphically the conservation of mechanical energy in an isolated system. If we have this piece here, this graph, energy is what we're measuring. And here we have two separate positions. Okay, as energy A increases, or position A, we start here, and we start moving. We're going to release energy. Okay? If we start out high here, and we come to a stop, this is EP. Okay, we had energy, now we have no energy. Here we had no energy, and now we have energy. The relationship between the two here, because this line extension is extra, Kleenex is beside Kyle if that's what you're looking for. I know. There's one over here with a bag. This line here then would be what we call the mechanical energy because it's the sum of the two energies. This line here going across. It's the sum of the two energies. In each of these spaces, there's 3 diagrams. Okay, so don't be big when you're drawing. I'll show you here. There's one here. All right. When we look at kinetic and potential and mechanical energy of a ball being thrown up into the air in an isolated system. So here's our guy, and he throws a ball up into the air. Okay? Here's his starting position, point A. This is just leaving the hand. This is the halfway point. And this point here, I'll just draw another ball here. This is the maximum height. Okay? The mechanical energy is the sum of the kinetic energy and the potential energy. So what would the value of mechanical energy be? So what would that be? We've got numbers, and I said that this was 10 and this was minimal. Okay, so 10. All right. When the ball is halfway up, this is position A, this is position B. When the ball is halfway up, it can keep going up or it can come back down. What would you say about the energy level of kinetic energy and potential energy? It would be what, Kyle? Max? They would be the same. So they would be roughly 5 joules because it can keep going up or it can come back down. It has options. And so what would my mechanical energy be? How much? 10. Okay, here we are at max height. What do we know about velocity at maximum height? 0. If velocity final is 0 meters per second, and I measure EK this way, what was my EK value be? Say what? Say it with confidence. 0. What's my potential energy then? It's all of it. In that very near instantaneous moment, it's 100% stored energy before it falls back down. Okay? So knowing that my EK is negligible and my potential energy is maxed out at 10, what's my potential energy, sorry? What's my mechanical energy? 10, because it is the sum of kinetic and potential energy. Okay? Is we're going to look at the kinetic potential and mechanical energy of a ball colliding into a spring in an isolated system. So here we have a spring, and we have a ball. The ball is moving this way to the left. This is position A. Okay? It makes contact and it's going to move the spring in 5 centimeters. Now I'm going to put a negative sign to show that it's compressing. Okay? So this is what it does. This is position B. And then in position C, we see that the distance compresses another 2 centimeters. Okay? Okay? So our mechanical energy, being the sum of kinetic and potential, is going to be what value? It's going to be 10. No potential energy because it's in motion, right? Okay? When we look at position B, it's hit the spring. The spring is compressing. What is happening to the ball? The ball is being slowed down and it has the potential to bounce back off the spring. So what we see is that maybe we're at 5. Nah, let's not say 5. Well, we want there to be an offset. Let's say that there's 4. The spring being compressed, its stored energy is what? Remember, the resting state of the spring is like this. So what can we say about the stored energy or the potential energy here? It's actually higher. It would be 6. Not much, because we've potentially collapsed this. The ball has collapsed the spring roughly 5 centimeters. So roughly halfway. Yeah, oh yes. And what do we say about the mechanical energy? It's the sum. It's going to be 10. Now, when we look at position C, we've compressed the spring 2 more centimeters. This spring is pretty tight. What kind of kinetic energy do you think that ball has? I wouldn't say none because we don't know that the spring is completely compressed, but it's definitely, let's say here, at 2. Okay? What do we know about the potential energy of that ball to rebound at this point with this level of compression? It's much greater, to the tune of 8 joules. And so then the mechanical energy is going to be stored, or 10, I mean, sorry. So I'm just going to move this around. Don't panic, I'll put it back. So what we see here in isolated systems, that regardless of what kinetic and potential energy are doing, the mechanical energy is always the same. So if this is 0 and 10, or 5 and 5, or 10 and 0, mechanical energy, if there's 10 joules of energy in that isolated system, there's 10 joules of mechanical energy. Can you close the door, please, Jen? Okay? In an isolated system, if the spring is fully compressed and the ball's not moving, or the spring is partially compressed and the ball has the potential to rebound off of it, in an isolated system, if there was 10 joules of energy in that system, in whatever relationship kinetic energy and potential energy have, the mechanical energy is going to be 10. Here's a diagram over here. A pendulum is pulled aside and then released. Okay, so this is pulled aside, and that's once it's released. It says determine the speed at the bottom of the swing. So what you need to know from here is that this distance is 13.0 centimeters. Okay? When we see a diagram like this and we see it comparing it between two positions, we're going to use the conservation of energy to help us solve this. Okay? At 13 centimeters. So what we know is that the mechanical energy of A is going to be equal to the mechanical energy at position B. It's conserved. It's comparing position A to position B. It's the same ball, it's the same string. We're comparing two systems. Mechanical energy is solved by EK plus EP. Okay, each position has kinetic and potential energy. Kinetic energy might be 0, but then it's all potential energy. But mechanical energy is the sum of the two overarching energies, kinetic energy and potential energy. Now in position A, the ball has not been released. It's being held there. Okay? Do we have kinetic energy? No. Rayleigh is saying no. Okay? In position B, at the bottom of the swing, so we know that it's just passing through, does it have potential energy? It's fully in motion. Rayleigh's taking a chance and saying no. Okay? So how do we solve for EP? What's the formula? mgh. And how do we solve for EK? 1/2 mv squared. Have we changed the ball in mid-swing? No. This mass and this mass, they're the same. It's asking us to solve for the speed, so we don't need direction, at the bottom of the swing. So if I want to rearrange this formula, the first thing I'm going to do is I'm going to bring that 2 up out of the denominator. So I'm going to get 2gh being equal to v squared. I'm just looking for v, so I'm going to square root my 2gh. So let's solve for that. 2 times g is what? 9.81. And the height is 13 centimeters. What's our base unit in physics? Meters. When I look at significant digits, this is the only value that we have because 9.81 is a constant. We get 3. 1, 2, 3. The 7 will play on the 9, so it's 1.60 meters per second. It just asked us for speed. We do not need a direction. So we went from a diagram and a question that only gave us one piece of information. And we probably all thought, how on earth do we solve this? But it's a matter of understanding the energies and what they are. A is 100% stored energy, and B was 100% kinetic energy. Okay? And because we didn't change the object, we didn't need to worry about the mass. A metal ball is fired from a gun that is powered by a spring that is compressed 21 centimeters. A metal ball with a mass of 64.57 grams is fired from the gun and into a 1.56 kilogram pendulum. The ball collides and sticks in the pendulum, causing the pendulum to be raised 9.3 centimeters vertically from its equilibrium position. Calculate the spring constant of the spring used in the gun. Okay, there is a lot of information in this question, so let's draw it out. We have a ball that's fired from a gun that's powered by a spring. So here's our ball. Okay. This is the spring in the gun. Here's our pendulum, our block of wood. It says a block of wood? No, it just says pendulum. And this is at equilibrium. After the ball hits the block, it does this. It's going to move up to the side. And the ball is lodged in it. Okay. This is position A. And this is position B. We're comparing two systems, or two positions is what we're comparing. Let's go through the information in the question and see if we can figure out what we need to do. So, Paulina, one piece of information from the question. Okay, what letter represents the spring being compressed? X. Okay, 21.0 centimeters. Avery, another piece of information in there. Right? Kyle, another piece of information. Okay. Cameron, another piece of information. Yep, that's what Kyle said there. Yeah, the height here that it was raised is 9.3 centimeters from the bottom of that pendulum when it moved up. Okay. And Daniel, the question is asking us to find what? The spring constant. So let's just start with what the question is asking us. What formula do we know solves for the spring constant? Yeah. So in some way, shape, or form, we need to get to that formula. Well, let's start kind of at the beginning. Typically, we work 100% backwards. We're comparing two positions. The position of the ball just as it leaves the gun, and then the position of the pendulum and the ball that's lodged in it after the ball hits it. When we look at two different positions, we're looking at mechanical energy. Okay? When we look at how to solve mechanical energy, we know it's the sum of the two energies together. Whoops. All right. When the ball is fired from the gun, hang on, let me read this. Calculate the spring constant of the gun, of the spring used in the gun. Okay. What is the spring right as that ball is being fired? Is it got all kinds of stored energy or is it 100% in motion? It's got stored energy. Okay. After the ball is released, the ball collides and sticks in the pendulum, causing the pendulum to be raised 9.3% vertically. So the ball goes up this way. The ball and the pendulum go up this way. At this point, at position B, are we all kinetic energy or are we all stored energy? What did you say, Avery? Kinetic. So here we're here, now we're moved up here. Just at this point, this like hang time point, it's potential energy. Okay, so like if we wanted to come back and look at our notes, we could call this the hang time. Okay, just to refresh our memory of why we picked EP. All right, how do we solve for the potential energy of that spring? Well, Avery already told us it's 1/2 kx squared. And how do we solve for the potential energy of the pendulum and the ball together at a height of 9.3 centimeters? MGH. Pardon me? Two relationships, and we're asked to solve x. The first way to do it is to move the 2 out of the denominator. Oh, sorry. Okay, you're right, Daniel. The first thing we have to do is move the 2. So we're going to get kx squared is equal to 2mgh. We're isolating for k. We're going to get 2mgh divided by x squared. When we look at these values, we have centimeters, grams, kilograms, and centimeters. We need to ensure, because energy is measured in a joule, we need to ensure that we're in kilograms, meters, and seconds. So this becomes 0.21 meters. This becomes, how do we go from grams to kilograms? Divide by 1,000, so 0.06457 kilograms. This becomes 0.093 meters. Okay? So then we can say that K is 2 times which mass? Well, this is on the pendulum side. The ball is lodged in the pendulum. So this mass is 0.06457 plus 1.5 kilograms. They're lodged together. We need that total mass because that's what's being measured at that system. Okay? One, what? Oh, you added them together? Okay, that's good. I just write it like this. I'm just going to leave it like this, but that's good. Did you guys get the same value that Avery got? And then my h, my height, 0.093 meters. And then I'm going to Yep. And then my 0.21 meters. Don't forget to square. Okay. This is the mass of the pendulum and the ball because they're lodged together. All right. When we do the math, we get what? 64.734882. And when we look at K being the constant, the spring constant, we know that that unit is newtons per meter. We go back to the original question and we're limited by both the 1.5 kilogram pendulum and the 9.3 centimeter. So 2 decimals, 7 will play on the 4. K is 65 newtons per meter. Okay. A roller coaster car has a speed of 1.5 meters per second at point A. What is the speed of this car? You need a diagram, and here's the diagram. Here's the roller coaster. And here's our little car with our little happy people. This height here is 12.0 meters. Okay. At the low point in the roller coaster, this height is 2.0 meters. And as it starts to go up the next ramp, this diagram is absolutely not in proportion. This is 0.40 meters. So it says a roller coaster car has a speed of 1.5 meters per second at point A. So this isn't the start of the roller coaster, it's already in motion. So the velocity at A is 1.5 meters per second, and the height is 12.0 meters. It says, what is the speed of this car at point C? So this is A, this is B, this is C. What is the velocity at C if the track is frictionless? H is 4.0 meters, HC. Okay, what are we doing? We are comparing two positions of the same object. Okay? When we are comparing the same object to two positions, we are going to look at the conservation of mechanical energy. And how do we solve mechanical energy? It's the sum of two, EK and EP. Okay, at the top of the track here, the car is in motion. It's frictionless, so there's no like pulley system at this point pulling it along to launch it. What do we have at the top of this track? Do we have EK, EP, or both? Both. It's in motion at the top of the track, and it has all kinds of potential energy to go over the curve and down into the valley. At position C, we're not at the end of the ride. Nothing is stopping us. Do we have EK, EP, or both? What are you hazarding a guess on, Avery? We have both. Yeah, because it's coming up, it's in motion, and it is at a crest of another hill. So it has the potential to go down, it has the potential to carry on, it has the potential. So we have both. So we have 1/2 mv squared A plus mgha is equal to 1/2 mv squared C plus mghc. That's what we have. Now, did these two people jump ship? Or did more people come into this roller coaster car? No, our mass stays the same. Okay, that we all agree on. What is it that we're looking for? We're looking for the speed at point C. So let's start rearranging this formula. There's a lot of letters and a lot of movement. We're going to have 1/2 VA squared plus GHA. We're going to move this guy over. What do we need to do? It's being added, so we need to subtract it. So minus GHC is going to be equal to 1/2 VC squared. That's the first step. We got VC on one side, we got everything else on the other side. Let's leave it at this point until we come to a number that equals 1/2 VC squared. Rather than trying to move the V or the 2 and square root it all, let's just solve it at this point. So 1/2, my velocity at A was 1.5 meters per second. I'm going to square it, plus 9.81 times my height, which is 12, minus 9.81 times my height at C, which is 4.0, is going to be equal to 1/2 VC squared. So what do I say? Now let's move the 2. It's way easier to go 2 times 79.605, and then we can deal also with the squared sign, so we can square root that all, and we get for VC. And we get what for a value? Meters per second, because we square rooted it. We got rid of those squares. When I go back to the original question, I'm limited by the velocity of 1.5, the distance of 4.0, to 2 sig figs. 1, 2. The 6 will have an effect on the 2. So VC is equal to 13 meters per second. So in real life, we don't ever work in an isolated system. We work more closely to a closed system. And a closed system is where matter can't leave the system. Energy can, but matter can't. And so this is when we see that there are external forces, in particular friction. So within a closed system, we have to be able to account for the loss of energy, heat, light. A prime example of this is a car accident. When two cars collide, not only is there the physical pieces that break off that we have to account for, but there's the sound of the collision that we heard. If there's a fire, there's heat. If there's a fire, there's light energy being given off. Okay, and those pieces we can't put back into the system. They're lost. And so what we say is that work is being done against the system. And one example of being able to represent it graphically is to do a closed system graph where we look at energy, which is measured in joules, versus two different positions. So if this is position A and this is position B, we see that the vehicle takes off, and so it starts with no energy and ends up in complete movement, whereas here we have another opportunity where it's coming to a stop. And we see that if we were to go straight across, this is what we should see for mechanical energy. But when we see this value here, like this loss here is work done against a system. Let's look at an example of that. When a bouncy ball is dropped from a height of 1 meter, the bouncy ball can never bounce back up to the initial 1 meter height. What we see is this pattern. Right? And so what we're seeing is that this is not an isolated system. We have energy being lost to the system where the bouncy ball comes in, it's compressed, energy is going out, and it's being required to come back up, but we never get quite that full amount back. We also have, when we spoke up at the beginning, in closed systems, the external force that we typically see is friction, so energy is being lost to air resistance. That is a form of friction. The deformation part, when it comes into contact with the floor. And we also see then that the mechanical energy decreases. Okay? What does this look like mathematically? Well, a 1,000-kilogram car is initially at rest at the top of a hill, and the hill is 15 meters high. It starts to roll down the hill. At the bottom of the hill, the car is going 15.5 meters per second. Is the system isolated or not? And explain the energy transformations that occur. Well, first thing mathematically, we need to decide on mechanical energy, and we're going to be looking at mechanical energy being the sum of kinetic energy and potential energy. So at the top of the hill, it's initially at rest, so there's no EK. Okay, so this is initial. At the bottom of the hill, we look at, again, or final, whatever, top final, EK and EP. At the bottom of the hill, it's in motion, so there is no potential energy. We solve this by looking at MGH. The mass of the car is 1,000 kilograms. The gravity is 9.81. And the height of the hill is 15 meters. And for that, we're going to get a value of 14,700 or 147,150 joules. Here, to solve this, it's 1/2 mv squared. So we're going to have 1/2 times 1,000 times 15.5 squared. And for this value, we're going to get 120,125 joules. So when we're looking at two systems, mechanical energy at the top versus mechanical energy at the bottom, we have 147,1500 joules. And here we have 120,125 joules. These are not equal. If they are not equal, it is a closed system. It is only in an isolated system where the energy input is going to be equal to the energy output, right? Neither matter nor energy can be entered or leave the system. However, in a closed system, matter can't enter or leave the system, but energy can. And so, to answer B, explain the energy transformations that occur. At the top of the hill, we said that there was only potential energy. Okay? As it starts rolling down the hill, now we're shifting gravitational potential energy. We're shifting it towards kinetic energy. At the bottom of the hill, the car is fully in motion. Therefore, it's kinetic energy. And so what we can say then is that some of the energy being lost, so why didn't we end up with 147,000 joules, is because of friction. Okay, so now stop and work on this last question of the question set. Make sure you've done the questions from the entire lesson, both the previous part and this part, and then we will be looking at doing a follow-up quiz.